Good morning. Is my voice audible? Yeah, just type Y in the comment because once I put on my headphone, yeah. So the screen is also shared, I guess. You can see the screen. Yeah. Okay. So what I hope is that you went through the DTW video and lecture that I have already shared on YouTube. You can go through that once again. Hope you got the gist of what DTW is. The main, let's say, difference between DTW and our previous, whatever we discussed, we were discussing about K-means and GMM, is what I call, or what you call timing information. Timing information. So let's say something like speaker. You want to identify speaker from somebody's speech, the identity of the speaker. There you have a lots of sentences, utterances from the speaker. You take out all the MFCCs and other features, and then you club them together, you jumble them together. It does not matter. It does not matter. Similarly, if you want to do some emotion recognition or accent recognition, you can do all that. You can do all that, but it will not affect. Even if you jumble up all these different features from different utterances, it will not affect at all. So the timing information or context information is not important in such applications. But if you have a piece of DNA code, genetic code, I think AGTC, I think, and AGTC, there's a code that follows. It has a sequence. You cannot just jumble a genetic code. Similarly, let's take any word. Let's say 9, for example. You spoke 9, so it has something like this will be your phonemes. Your phonemes will be something like this. It's not exact, I don't remember, but this is how you will pronounce. These are the individual sounds. You cannot jumble up all this and expect that the speech signal will be the same. If you put this one here and again exchange or the order, you will come up with a completely different word. So the timing information or contextual information is really important in applications such as speech recognition. So in DTW, we had a very simple way of dealing with this. We match two sentences and we want to find out at what time one sentence should be matched with another moment of. It never goes back. It always goes forward. The DTW algorithm, any sentence that you match, if you take sentence, the frames of sentence 1 here, sentence 2 here, any sentence, whatever the path it is, path never goes like this. The path will never go like this. It will never come back. The path will always be forward moving. So the time is moving forward. Now, a better way of dealing with this kind of uh, applications where timing or context is important is to involve statistics, to include statistics. And this is where you will come across Markov models, and in particular for speech and other applications, hidden Markov models. So what essentially is happening is, when we give our objective in speech recognition or automatic speech recognition is, you will give features derived from the speech signal to an algorithm, and it should produce text, written text. So it is called speech to text conversion. That is the goal of automatic speech recognition. So what we generally give is, we give all these MFCCs or other features to the algorithm. These are your what is called observed variables. This is what the machine, the algorithm can see. This is what you give to them. On the background, there is a hidden variable. These are actually your sounds, individual sounds that the machine is not, machine only sees numbers. But on the background, these sounds are there. These hidden sounds are there. And the machine has to find a way to correlate each of these observed variables, these MFCCs, these features, with those individual sounds that it cannot perceive. For it, it is some abstract state. Something abstract is there. It has to find out a correlation. That is what HMM is all about. So to understand HMM, there is a very it is better to start with a simple example. So I have selected a video, which is a very good video. It gives a description of HMM based on weather and somebody's mood. Weather and mood. I want you to watch this video today. It's a 30 to 33-minute video. Watch this. And then tomorrow, if you watch this carefully, you will understand what HMM is all about. Then tomorrow we'll go through a very mathematical formulation. It will be very involved. It will take 1 or 2 hours, the whole mathematics. And it's a very important step if you want to be a machine learning researcher in speech technology or voice technology, and even other domains of research in genetics and other places where you need, or natural language processing also, where you need contextual information. Let me give you a simple example of what contextual information is. If I ask you the sky is what? Just fill in the blanks. What will pop up in your mind? Most probably the sky is blue will pop up. Now there could be other options also, gray and also, but the probability of blue is very high. So if you start typing in Google search the skies, it will automatically start filling up your sentence. However, let's put it, today is, it is raining today. The skies, now what will happen? Now blue's probability becomes much less. Most probably gray will come up as a high probability. This is called contextual information. In fact, this you can say is local context. This you can say is let's not say local, short term context. This you can say is long term context. In fact, this is a very good example for neural networks, something called recurrent neural networks, and this is a very good example of LSTM, long short term memory. But these same concepts actually are there in HMM. It comes from HMM. So let's watch the video, and then we'll go ahead with the mathematical formulation of HMM next class. So I hope you are almost finished uh, whatever lecture was shown in the video. It's a very good video. Go watch it once again, because this will be required. These concepts you must be crystal clear before we can go to the mathematics tomorrow. Tomorrow you don't need to come physically to class. From 9 to 11 we'll have online class. So you were able to watch my screen, I think in your classroom. Long time ago I had shared some useful subject material. So in that, the last one, there is a free article available, a tutorial on HMM and selected applications in speech recognition. I have it's freely available on the internet, but you can get it from that link also. Download that and go through the basics, first few pages, however you can, how much you can understand. Go through that so that we can one go cover all the mathematics tomorrow. It will be really useful. All the notations I will use from that. The same thing is mentioned. This is also by Rabinar, also by Fundamentals of Speech Recognition Rabinar. In one of the chapters, the same thing is mentioned. It's the same author. So please prepare yourself so that tomorrow we can uh, go through the mathematics behind HMM. So that's it. Please give your attendances, and then you can exit the lecture. So again, hello everyone. We'll discuss about HMM and the mathematical formulation of HMM today. So you have seen yesterday's lecture and a video that I shared on HMM using a simple example of a hypothetical example of a person having happy mood and sad mood, which are the observed variables, observed states, and the hidden states being what's the weather around his place in his hometown, whether it's rainy, cloudy, or sunny. So what happens in HMM is, or hidden Markov model is, you have states. You have a set of n states at any particular time t. At any particular time t, we have a possibility of any of these n states. At any particular time t, we could have S1 or S2 or some Sn states, and we say Qt equal to any one of this. Qt will be any one of the states at time t. Then from Qt, whatever Qt we have, from hidden state we have, we'll get an observation, OT. Now we'll discuss discrete HMM here. We'll not go for continuous HMM. So in discrete HMM, we'll have a set of, just like a fixed set of states, finite states, discrete and finite states, hidden states. We'll have discrete and finite set of observations. This OT could be anything from a set V. If this is a hidden set S, you can say this hidden set V from V1, V2. Some VM possible outputs are there, observation states or output states. Or observation symbols. So from any hidden state Qt, you will get an output state or output variable or output observation OT. This OT could be any one of these V1, V2, VM, these M states, and this Qt could take any one of these states S1, S2, and this happens at a particular point of time. We are saying at a particular point of time there is a hidden state. From that hidden state an observation is generated. These are the possible hidden states, these are the possible observations. Now how does an HMM work? So what happens is, let me insert a page here. Let's denote this as the time axis. So t equal to 1 to t. So there are observations 1 to 1 to 2 to OT. Let's say this is a set of observations. We are looking at a length t. These are produced by Q1, Q2, Qt. Now this could be any one of this. Sorry, this is Qt, this Qt, OT. This could be anything, as I said, from the set S, S1 to Sn. And this could be, of course, again, let's put it like this. This could be anything from V1 to Vm. And what happens is, from a particular state, any S1 state, at time, let's say Si state, to time t from the and time t plus 1, there is a particular probability of jumping from one state to other, which we call Aij. Is Qt equal to Si, Qt plus 1 equal to Sj. This is a particular probability. And similarly, there's a particular probability that from a state Si, any state, is Qt equal to Si. What is the observation? OT equal to, let's say, Vj, or there is a particular probability of this. So which we call Bj from state I, or Bi, let's say, from state I to J. From state I, we are getting an observation Vj. We also denote this. We'll also use the notation Bi OT in many cases. So let's see. Yes. So what we have is Aij. So at a particular point of time, if we have a state Si, in the next instant, next time instant or next frame or whatever index you are using, if your state changes to Sj, then that probability is denoted by Aij. Similarly, once you are in a particular state, you can have m different observations, outputs. Yes. So what is the probability that the output is Vk? That is denoted by whatever is your state, we denote it by that Bj. If Sj is your state, we denote that J index here. And K is given by the output, whatever observation you are getting. We also denote it, as I have said just now, we also denote it by this notation from time to time. In fact, this notation is more used, you will see. And then we have a initial distribution. See, we know from one state to one another state, how will we jump? We'll give by Aij, some Si to Sj. We also know from Sj there is a probability here for whatever OT you get, or we say Vk, this will be your Bi K or BIOT or BJ OT plus 1. This is T plus 1, OT plus 1 or BJ K. We know all this. But what is the initial probability of the initial state? You start the observation O1, O2, O3. What is the probability of the initial observation? We need that as well. There are, sorry, initial state. There are n possible states. What is the probability that the first observation is generated by the initial state, or the initial state out of those n states, that the first state is Si out of those? This is given by this pi, denoted by pi. So what you have is, what your machine sees is a set of T observations. These T observations are nothing but, let's say in your case, MFCC vectors. TMFCC vectors, 39 dimensional MFCC vectors. You can say there are T frames are there, continuous frames. You spoke a word, T frames you got. Each of these frames, you extracted features. Those features are there, 39 dimensional features. Those are your observations. Now, your hidden states are nothing but what are the sounds, individual phonemes that produce those. So an interesting thing to note is here, what is happening is, or maybe I have drawn this previously. Yes. There is a particular probability of going from one state to the other. Maybe I will use, there is a particular probability from going from one state to the other. And it is reversible. It may not be, but there is always a probability, Sij. Similarly, Aij, Aji could be there. Means at any point of time is T, one could go from Si to Sj and the next instant. One could also have this Sj, it was there, Si. But if you look at the observations 1 or 2, we have not stated any transfer from OJ to OK. Nothing we have mentioned like that. So the observations we have kept independent of one another, but we are indirectly linking them through the states. Through the states, we are linking them. We do not link the observations directly, but we are linking them through the states. We are saying from one state to other, we have a particular probability of moving, but we are not saying that one observation to other there is a particular probability. So we are indirectly traversing this path, and in this way, we have an indirect path, indirect link. So, as you know, speech or other signals which have contextual information, these phonemes and all the words are they have kind of a correlation when we speak a continuous word. If you are speaking just a single vowel ah, or that's a different thing. But when you are using continuous speech, there is a correlation between the word sequences. So this is the way in which we get the correlation to the hidden states. And this formulation makes the mathematics much easier. We could also have made a Markov model. It's called a Markov model instead of a hidden Markov model because there are no hidden states. We could also have developed a Markov model by using correlations or linkages between the individual, but that would become a very mathematically complex model and unimplementable in many ways. This has more flexibility and has become the standard in speech recognition. Anyhow, coming to the topic, yes. So, how are we going? What is going to happen is O1, O2, O3. We have 10 T observations here. So, how are they generated? You have to think it like that. At a particular time T1, there was a state Si out of those n states. From that, from Si, that Q1, we got an observation O1. How? Because we have a oh, sorry, yeah, uh, yeah, this is Bi. The state is I. So what is the observation O1? Or we denote it by Bi if O1 equal to K. Then we go to a new state from Q1, Q2. Then we have another probability of observation being generated from that state. And like this is continuous till we reach all observations. So what we have finally are three things. Two matrices A and B and a vector pi. What is this matrix? This is called state transition matrix and this is called emission probability matrix. If you have watched yesterday's video on HMM, then you will already know what I'm talking about. This state transition matrix is this. It gives from a particular state I to particular state J. What is the probability of moving from one state to other? From moving from one state at a time t to another state in a time t plus 1. What is the probability? That is given by this matrix. A. The other B is again from a state I At a particular point of time, you are in a state I. Sorry. And there are observations. When you are in a particular state, you can generate an observation. Those observations have m different choices, v1 to vm. What is this? Vk. What is the probability that when you are in state I, the observation generated is Vk? That is the matrix. We have discussed about this already. We are putting all this in form of a matrix. And then pi. What is the probability that your first observation, sorry, the first state, Q1 equal to this? There are n states available. Out of those states, Si, the Si state, your first state is Si. What is that probability? So you put it in a vector. That is what pi is. So we'll use the symbol lambda to denote this HMM model. It consists of that matrix A, matrix B, and pi. So this is the complete parameter set of the model. So there are three basic problems for HMM to solve. First problem is what we call as testing problem, or problem 1. Second is we'll go one by one. Let's go to the testing problem. What do you mean by testing problem? So you have this model, you have built an HMM model, A, B, pi, you have somehow figured out. Let's say you are doing something like word recognition or digit recognition. You utter the sounds 0, 1, 2, whatever, 1, 2, 3, like that. For the sound, for the word 0, you have built a model, lambda 0, with A0, B0, pi 0, let's say. Again, for 1, you have built a model. All this you have built somehow. However, how you have built, that's a different story, but you have built. Now you are testing. You have an observation. You uttered something. You uttered one of these words, let's say. One of these numbers you uttered. So you tested. You are testing. You got a speech signal. From that you extracted features. And you got a length. Certain length you got. Certain sequence you got of vectors. MFCC vectors, let's say. So these are your O1 to OT you got. Now you will put it into each of them. And you want to find out what is the probability that is observation belongs to each of these models. What is the probability your observation, let's say this is your observation, O belongs to lambda 0. What is the probability that O belongs to lambda 1, and so on. And whichever probability is the highest, you will say my testing utterance belongs to this model, the 0 model. That means I uttered 0. The machine will say whatever this person has uttered, this speech signal, it corresponds to 0. He is speaking 0, or he is speaking 1 or 2. Out of all this, you'll compare. But the first thing is, the important thing is, how do we figure out what is the probability of the observation given the model lambda? But that is the first problem. The second problem is, let's again, what is it? Yeah, sorry. Yeah, the second problem is Given the observation sequence and the model lambda, how do we choose the corresponding state sequence, which is optimal in some meaningful sense? Yeah. So the second problem is, yeah, we have this lambda model. We have this lambda. We have already somehow figured out all this a b pi. We have got somehow, and we have an observation sequence. What observation sequence is there? Let's say during testing, we put this observation. So we uttered as, let's say, speech signal and whatever, we have this OT observations are there. I want to find out what is the most probable hidden states. What is the sequence of hidden states that produce this? What is the sequence of hidden states that produce this observation? For this given model, for this particular given model, what is the sequence of hidden states that produce this observation? I want to find out that. That is my second problem. Problem 2. And lastly, what we have is the training problem. So the training problem, you have to figure out A, B, and pi. So what we do in any machine learning algorithm, we start with some initial random assumptions of A, B, and pi. In the video you watched yesterday of the simple HMM, it was very easy. It was a crude way of assigning A, B, and pi, small set of observation. It was a very hypothetical and simple example, too simple. Let's imagine you want to figure out which sound in case of A, one state to another. Let's say which phoneme or sound comes after the previous phoneme or sound. There are so many, depending on the type of word and whatever. You have to go through so much data to figure out these matrices. So there has to be a certain recursive or better efficient way of finding out A, B, and pi. So that we will discuss. What is the probability? Sorry, what is the, yeah. So what we want to do is we want to, yeah, maximize during training. If you remember GMM, we also do something similar. All machine learning algorithms have something similar. We have an observation. We have an initial estimate of lambda, some initial estimate we have. Lambda equal to lambda initial. We have an observation. We try to maximize this. Whatever observation we have, training data we put to we are hoping to maximize this observation. So we tune the model parameters. You tune it. So you get some lambda 1. Then you again tune it so that you maximize the observations from the training data. This is a training problem to figure out A, B, and pi. That is the training problem. We have already done, for example, in k-means, we had what randomly we initialize the means. Then we found out which points belongs to which cluster means and all that. Then we again change the cluster means and again. Similarly, GMM, we either have a randomly initialized covariance matrix and means, or we use k-means to get the initial estimate. Then we change, adapt, and finally we get uh, what is called a model, which is let's say saturated model or a convergent model, so to say. So these are the three problems. Now we will discuss each of them, how to get the solutions to each of the problems. So just a minute here. Am I audible? If I'm audible, please type Y. I did not. If there is any problem, please let me know. Okay. So now, solution to problem one. So we have an observation. Given the model lambda. We know we have certainly, this is a testing problem. Remember, this is a testing problem. We have a model lambda figured out. We have a testing problem. So what we need to find out is what is the probability that this observation was generated by this model. Probability of O. We write probability given by lambda. That's a standard notation. But you can simply also write probability of O given this set of parameters A, B, and pi that we know. But this is the standard notation used. So the now each observation is generated from a hidden state. Each observation is generated from a hidden state. So from Q1 you will get O1, Q2 you will get O2, Qt you will get OT, and Q1 has n possible states, Q2 has n possible states, Qt has n possible states. So there are, if this sequence of states you say, there are n to the power t possible sequence of states. Now let's take one fixed state like that. One fixed state. Let us say out of this n to the power t possible sequence of states, one state you take. So that we are saying, let's take one that's state, consider one such fixed state. Okay, out of this n to the power possible states. So when you do that, we have the observation already. Let's see what the observation probability of the observation is given Q. Forget about this lambda. This is just for notational convenience. Okay, forget about this lambda for a moment. Okay, so P of O given Q. Now we have already established that we do not have any relation directly between the observation. We have a relation indirectly through the states. So the observations we can simply consider as independent of one another. So if you have Q1, Q2, Q3, or you know the state sequence, what is a probability of observation? Just multiply. Because in our HMM, we do not consider the observations to be directly dependent on one another, having any. We have indirect link through the hidden states. So this, what will this be? Whatever the Q1 state is there, whatever Q1 state was there, we denote it like this. And this is the output O1. this is a multiplication. So there are t multiplications here. T values we are multiplying. Now let's find out. So we have found out a for a particular sequence. This is, let's say, some particular sequence q star. We have found out that is what it is. Out of n to the power t possible sequences, one sequence we took, and that is what we found. Okay, this is your really what is called mathematical expression. Now let's find out what is the probability of that q star I am writing here for your convenience. In that. So that for that particular sequence. So pi first state. So q1 to qt first state is what? We already get what is the probability of the first state being q1. This is what we denote it by pi. Then we jump from q1 state to q2. Aij. We were using the notation from Si to Sj. Here we do not know what is q1, q2, or for notational convenience we are going to use this like that. So here again there are t multiplications. Remember, there are t multiplications here. Now, why is all this important? So we are finding out for a particular sequence, state sequence. So what we found out? We found out probability of this particular sequence, basically. Forget about this lambda for a minute. Okay. We found out the probability of this particular sequence, let's say. So what is the probability of O? Probability of O is probability, if you have revisited Bayes theorem, is into probability of Q. This is the probability of the observation. Sorry. This is the probability, joint probability of the observation and the state, that particular sequence of states that we are saying. For a moment, forget about this lambda. Forget about this lambda for a moment. This is Bayes. And how do you get probability of O? If it is a joint distribution, if you want to get a marginal distribution, how? You get sum it. Sum it, a variable that you don't want, you just sum over it. So if you sum this, just forget about this lambda for a moment. Just neglect it. If you sum for all q, all possible q, how many q's are there? N to the power t possible q sequences are there. If you sum them, you will get the probability of O. The probability of the observation given this model. Now I'm sketching off here this lambda for your convenience so that you understand. But remember, this notation you should keep as it is. I've shared the document with you as well. So there are t multiplications here, another t multiplications here we have seen, and then n to the power t sequences which have to be summed. It's a huge mathematical operation to do like this. So there are, see, 2t multiplications to be there. Sorry, yeah. In total, if you look at the uh, calculations we have to do, we have 2t minus 1 to the power nt multiplications and nt minus 1 additions. This is a huge mathematical operation. You have to do it in the standard form. There's a very, very simple example here given. N equal to 5 states, t equal to 100 observations. So 10 to the power 72 computations you would need. So this is not uh, a possible implementation. So we need some recursive formulation, some way to do it in a much more efficient manner. This is where we come to this, the first solution, which uses this forward procedure. It's called a forward backward because there is a forward procedure as well as a backward procedure. We'll not use the backward procedure. We'll use simply the forward procedure. Why is it called a forward procedure? Because we'll use a variable called a forward variable, alpha ti. So see what alpha ti is. Alpha ti is defined like this. You have till tth observation, you know what the observations are, and you also know at the t at the time t only, whatever is your state. Now let's see how we can get this. From one variable, how can we get to the next variable in an inductive or recursive formulation? Let's try to figure out this alpha t plus 1j. Okay, so alpha t I equal to probability of O1 to OT, QT equal to SI. And there the slash lambda is there. Let's forget about that slash lambda for a minute. Okay. There is slash lambda is there. Let's forget about that. So this is what it is. So alpha t plus 1 j, probability of O1 O t plus t OT plus 1, and we don't know about whatever QT is, but let's imagine, no, let's put it this like this. Let's put it now you have QT plus 1 equal to J. That's it. You know all this. Let's insert another. Let's put another, this QT equal to I, QT plus 1 equal to J. Let's insert this. Now we know, say, if you look at this is a joint distribution having extra variable, and this is like a marginal distribution where one, this QT equal to I is removed, it's not there. So if you sum this over I, where I is your number of states, QT equal to, I should write SI, sorry. There are states or n states. If I sum it over, I will get this. Now, how do I get this? How do I get this? So if you break this up, see from O1 to OT, QT equal to SI, I know this probability will be alpha I, sorry, yeah, I, alpha T I. Then I have this information that OT plus 1 was generated and QT plus 1 was SJ. So I jumped from state I to state J, and this is the probability. After I jumped to state J, observation I generated was OT plus 1. So I was in state J and OT plus 1. So this is what, this is how you get a recursive formulation. So now let's go back. Yes. So here you will find, yes. So we have this definition from alpha ti. We found a recursive formulation. Now, what is the forward procedure? Alpha 1i initialization. What is alpha 1i? Alpha 1i is P of O1 Q1 equal to Si. Given lambda is there, forget. So what is the probability your observation 1 was generated and you know that state is, first state is Si. So obviously this is pi of I. What is the probability that the first state is Si? And then if your first state is Si, what is your observation? If you know alpha 1, then you can get alpha 2 this because of this recursive formulation. And then you have, how do you find the probability of the observation? This. So let's look at this. How will we get it? So alpha t. Let's say alpha t. I will like to maintain that stem. Yeah. Let's say alpha ti. Let's say alpha ti. What is alpha ti? Probability of OT given QT equal to SI. And this lambda I am just removing here. I am not denoting it for convenience so that you can understand what's going on. So this is a joint probability of the observations given the last hidden state is Si. So if you sum this up over I, if you sum this up over I, you will be left with only the probability of the observations O1, O2, OT. So this is how, in a very efficient manner, we can get the solution to the first problem, that is to test the HMM. Given an observation, what is the probability that this observation belongs to this model? This model lambda given by these parameters A, B, and pi. So the first step is done. We'll now go to the next step. The next step is to find out the hidden states which generated my observations. So we want to maximize this probability. Again, just for your convenience, don't pay much attention to this comma lambda. So We want to find out, we want to maximize this probability. There are, as you know, O1, O2, OT sequences, so Q1, QT sequences, and each of them has n possible. So n to the power t possible sequences are there, which hidden sequences which could have generated this observation. We want to find out the optimal, the best one. How? The one which maximizes this probability. What is the probability of this hidden sequence given the observation that we have? So this is given by a very popular algorithm, Viterbi algorithm, and it has similarity with, if you pay close attention to it, we discussed about dynamic time warping in our previous lectures. It has a little bit of similarity with this. Because in dynamic time warping, when we are building that cost matrix, at every point we are finding out which best path to take, which is a minimum distance of my previous point in the path. Something similar is going to happen here. So, sorry. Yes. The Viterbi algorithm. So, we need is the solution to problem 2, finding the hidden states. Now, what we need to, we said we need to maximize this. Now, this is, as you know, probability of Q comma O divided by probability of O. So maximizing this is same as maximizing only this, neglecting this. The probability of this observation, given so many possible observations, this is like a constant in this case. It's not going to affect anything. So maximizing this conditional probability and maximizing this joint probability is the same. So we will in turn maximize this instead of this. It boils down to the same thing. So we define a parameter, this is the parameter. Yeah, we need to define, because again, you see, in all these cases, there are a huge number of possibilities. Entity poverty we have discussed previously in the forward algorithm. If we want to do in the straightforward manner, how many computations we will require. Same thing will happen here. So we need a recursive procedure. And so we need to define certain variables for that. So we have defined a variable, this delta ti. What it says, you need to find the maximum, the best Q1, Q2, Q2 till Qt minus 1. You have to find till here the maximum state sequence. We know that at this point of time, this is the state sequence. You have to find the previous t minus 1 state sequences. And we also know till this point of time, what are the observations. So this is the relation we will get if we recursively. Let's try to figure out this relation. So what we have, delta ti we have to maximize the probability of t minus 1. We know qt equal to si, and we know all these observations till st. I am removing this slash lambda here for convenience, okay? But when you formally write, please include that. But for understanding, it's better to remove it. So this is what we need to maximize. What we need to find out this These state sequences we have to find out which maximizes this probability. So this is the parameter like that. Then del t plus 1j, what is that? Obviously, now we need to maximize till t, probability of, let's say, qt minus 1. Let's write qt here. We don't know qt, let's say. And you qt plus 1 equal to some sj. And we need know all this ot plus 1. Right. Now we already know till t minus 1. Till t minus 1, this gives us the maximum probability. Till t minus 1, give this as the maximum probability provided qt was si. So this, if you include qt also here, the only difference, so it will be like maximum of I. You have to figure out the best sequence out of n possible. Maximum of I del ti. This will give you this. Then from qt to qt plus 1, you jumped. You jumped. But you were in state I. Remember, you have to maximize this. Okay, you were in state. You jumped how? Where? From AI to J. This thing you have to maximize. And once you are in J, you produce output T plus 1. That is BJ OT plus 1. So this is the recursive relation. Once you understand this, you will have to give a little bit of effort, but it's quite straightforward if you are comfortable with the basics of probability. So once you get this, then things become quite straightforward. So this is your relation, recursive relation. So let's go then. So what you will do? What is delta 1i? Delta 1i is, what was probability of, q1 does not, is a maximum of, if you see, maximum of q0, that does not mean anything. So what delta 1i is? Probability of q1 given O1. That's it. Or probability of q1 equal to I given O1. That's it. q0 does not exist. So probability of q1 equal to Si given O1. And you already know this is what will happen. q1 equal to Si pi 1 and probability of observation 1 given. This is it. And the state sequence here, well, there's nothing to say about this. This is, we are tracing the, it is like initial. We are not getting anything. We are starting from first position. Then recursive, we already know, we have just figured out. And this previous, this maximum, if you look at this recursive formula, this is the part where we are I that we are maximizing. Basically, this becomes like a constant, and this gives actually, this part actually gives which state you are going. Which state you are going next. This is the part which will give. And you know the difference between max and argmax. It is the same thing. If you could have written this whole thing also, does not matter. Argmax is finding out the argument which maximizes this probability, this function. Max is just what is the maximum value. Max and argmax. This is the maximum value that you will get. And what is the argument that you are tuning? What is the value of the argument? This is what keeps track of the uh, next part, next what is called state, and this is you are getting that overall probability. What is the maximum value? So finally, you get this. What is del ti? Del ti will be, if you see, what is the definition? So del ti, probability of you max till qt minus 1, probability of all this q1 to qt minus 1, qt equal to si and ot. So if you maximize I, that's your overall maximum. Only thing here not maximized is this part. If you find out the maximum over I, you will get your final entire sequence. That's what it's written here. And again, if you put that, this argument, you use this argument, argmax of that, you track that, whatever was the maximum. And just like in DTW, you can trace the path. That's why it's related to a little bit of dynamic programming. You can trace the path wherever your maximum probability is. At every point, you have n choices, basically. In DTW, you're having 3 choices in simple DTW, but there were multiple paths. So similarly, here you have n choices at every point. So you track the best path and you will get the entire state sequence. So the most important part, again, in all this is figuring out this recursive formulation. So that ends problem 2. How to find out the hidden states. The best sequence of hidden states which generated my observation. third part now is the training problem. The training problem, how to determine the model parameters to maximize the probability of the observation given the model. This is given by a famous algorithm or famous procedure called Baum-Welch. So we had previously defined alpha t. During your forward procedure in the solution one, we define alpha t high. Yes, probability of, I think, OT given QT equal to SI slash lambda was there. I think that's what was it. Let me go back and see once again. Yes, that's what it was. Now, the forward is a first problem, testing problem, could also be solved using something called a backward variable, but we don't use it. We use it for another purpose. This solution to problem 3, we use it for that purpose. But the backward variable is defined like this. See here, till t and qt equal to si, we know. Here from t plus 1 to ot, we know qt equal to, given qt equal to si. Again, qt equal to si, we are given. And what is the probability that the observation starting from t plus 1 to the last observation? That is what is the backward variable. And you can figure it out yourself, just like the forward variable. It's quite simple. You will get a recursive relation. Just like the forward variable, you will get a recursive relation for the backward variable. Why is it called backward? You see, you start from the end and come to the first observation. So alpha t plus 1 has a dependency of alpha ti, but here you see, you to get bti, you need these backward variables from the future observations. So anyhow, you can figure it out yourself. This is very simple. If you know how to do alpha ti, as showed you, you can easily do this bt variable, how to extract, how to find the recursive relation. So important thing is to remember what this part. Now we need another variable, zeta t ij. What is it saying? We know that a point at a particular time t, the state is I. At a particular time g, the state is a particular. Then the next time instant t plus 1, the state is j as j. So we need, and given the full set of observations q1, o1, o2 to ot. So let's figure out how to get a recursive relation for this. So what we have, I think zeta, let me see, zeta t I comma j. Yes, zeta t I comma j is probability of qt equal to si, qt plus 1 equal to sj, and given the observations. I'm removing lambda for, let's say, to avoid confusion, or make it easy for you to understand. So this is, based here, qt equal to si, qt plus 1 equal to sj, comma o divided by Probability of observation. Now, again, this above whatever is there, qt equal to si, qt plus 1 equal to sj. Oh, again this same thing, qt equal to si, qt plus 1 equal to sj, comma o. How do you get this? This is a joint distribution. If you sum to get the marginal distribution, you just sum over whatever other variables are there, random variables are there. So this will give you probability of the observation. That's how you get it. Now let's figure out this part. What did this one say? What is alpha ti? Alpha ti is this all the entire observation till ot. Alpha ti is all the entire observation. If you see, alpha ti is all observations and qt equal to si. We know that. So let's write this because all observations are there. Alpha qt equal to si we know. So it will be alpha ti. Definitely alpha ti is sure. Then we have what? Beta t. What is beta ti? Given qt equal to si, we have all this from t plus 1 to t. So this is definitely going to become here j. Beta t plus 1. I think beta tj or no, sorry. Yeah, sorry. This is ot plus 1. So let me write this as, let me rewrite this as, so beta t j, I think t plus 1 j it might be. Let me see. Yes, because t means qt equal to si. So t plus 1 j. Plus qt plus 1 equal to sj. But in between that, see alpha t has all O1 to OT and QT equal to SI. This information is there. Beta T plus 1 J means T this OT from OT plus 1 to OT you have the information, and QT plus 1 equal to J you have the information, given QT plus 1 equal to J. So there has to be a transfer from this to this. So there again Aij is required. A transfer from state I to state j. So finally you get this. And I forgot one thing. In the last, once you are in state j, you are emitting this, this called, once you are in this state j, you are emitting OT plus 1. I forgot that. You have to include that as well. So you have information OT plus 1 to OT given QT equal to SI. You don't have then you have information that OT plus, because beta T plus 1 means observation starts from T plus 2. I forgot. OT plus 2 to OT. All future observations, and but you know that QT plus 1 is J. So Aij, there is a jump from I to J. You have to figure that out. And OT plus 1, how was it generated? Since you jump from state I to state J, you know that. And qt plus 1, you generate an observation ot plus 1. That you have to include. So you are in state j and ot plus 1 observation you generated. So that's included here. I forgot. So this requires a little bit of deep thinking, and you will have to go through this a few times. It's not, you have to in fact practice it really. But once you get this, I have already explained to you, if you sum over, you will get this marginal distribution probability of the observation. So now we need another parameter. It's getting fun. So what was zeta t I comma j? Probability of qt equal to si, qt plus 1 equal to sj, given the observation, and lambda was there. Let's, as I said, I am not worried about including lambda at the moment. So this is it. We have a parameter, we define a parameter, this gamma t j, which is like qt equal to si given the observation. Obviously, you can see, easily see. Again, how to get this marginal? Here, zeta I and j, this extra term is there. Just sum over this extra term. You will get gamma ti. And what is gamma ti? Given all the observations, at time t, what is your state? Probability of state, si or sj, whatever is written there. So this is the probability. Remember, probability of qt equal to si, gamma ti. This is gamma ti. Probability of qt equal to si given that observation. So obviously, from this qt, this si, you have to transition to another state in the next time instant or next observation. So if you sum over all the time instants, you will get what is the kind of average number of transitions from this state si. Again, if you sum over this zeta ti, what is the definition of zeta ti? You are in time, in time t, you are in state si. In time t1, you are in state sj. If it sum over all the time instance, you will get what is your kind of estimate of number of transitions from si to sj. So if you get that, first, it's really easy to see why this is expected number of transitions from state si to sj. This is zeta, just now we discussed, and number of transitions from state si. So this is the definition of aij. What is the probability that I will transition from state I to state j? From at time t1, t I am in state I, at time t plus 1 I will be in state j. What is the probability? This is how we will figure out. Similarly, bjk, at I am in state j sj. What is going to be the probability that I will output an observation vk? And again, remember what gamma t here, they're using the variable j. Yeah, gamma t j, what will be that? Because Remember again, this definition should not forget. So P, you can even say, okay, Qt equal to Sj given the observations. And when you sum it up, simply sum it up. Expected number of times in state J. So you will transition from state J, obviously. So that's how it is. But observing the symbol Vk such that, here it is mentioned, such that OT equal to Vk. So you are in state J, what is the expected number of times you are in state J, and observing symbol K. So at those times, whenever this Vk symbol was emitted, you consider only those summations. And bottom is expected number of times in state J. Now, interesting point between this Aij and Bjk. See here, the summation is t minus 1, t minus 1. But here summation is t. Why? Because these are considering transitions. And when you are in t, you are not going to transit to any other. Your observation is complete. Only from first observation to t minus 1 observations, you have a chance to transit to another state. So remember, that's why here t minus 1 is here. On the other hand, output you can emit without any such restriction. You can output, given any state at any point of time, you can have an output. So here the entire summation is from 1 to t. This is what, when you are talking about transitions, t minus 1, remember this. And finally, this initial state probability. Again, come back to this. What is this? Gamma tj or gamma ti will be, again, this is just a variable qt equal to si comma 0. So gamma 1 equal to probability of q1 equal to si given the observations. Even your observations during training, this is your observation data. What is the probability? The first state is si. So from that you get gamma 1 So what happens is you initialize pi, aij, bjk. That's why there a bar is given on top. You initialize with something. You have a model. Then you have, let's say you uttered a word. You are building an HMM for that word. Maybe a digit 9 you spoke or 10 you spoke, something, or 1 you spoke. Whatever features or you extracted from that. Based on that, you will now tune this model with all this. You'll find this pi bar, aij bar, all that. Then another same word you spoke or somebody else spoke another time. You will do it again, tune it again, again, thousands of utterances of the same word. You will do it till some kind of saturation happens in these parameters. So that's all. So the same thing I was mentioning. If we define a current model as this and we use this right hand side, whatever, we re-estimate the model. It has been proved by the Baum-Welch algorithm, it has been shown that the initial model defines a critical point of likelihood function, in which case lambda means it's a saturated. Otherwise, this is anyhow the model, whatever new model you are extracted from a new observation of that same thing, same class of data, is it will always be better than the old. So these are the three problems in HMM. First is testing. Second is finding out the best hidden sequence that could have generated, the most probable hidden sequence that could have generated these observations. Third is how to train the model, how to figure out the parameters of the model. These are the three main aspects of HMM. So you will, that's why I showed the video yesterday. I know this is a more mathematically involved. So you'll have to devote some time into each of these equations that we have gone through. Is something that will require effort from your end. So please go through this. You can rewatch the lecture whenever you want. As you know, I have uploaded, I will upload. So I guess there is no questions. So you can leave the classroom and we can conclude the lecture. Thank you.